All right, ladies and gentlemen, I want to introduce you to Daniel from Dielectric. He is going to be doing a building reliable broadcast systems. Daniel began working with Dielectric as the international sales manager in 2021. In his previous position, he worked in the broadcast industry, first as co-founder at the Professional Broadcast Supply from 1992 to 2013, and then as the Latin American sales manager at Broadcast Electronics from 2013 to 2021. For the past 33 years, Daniel has been involved in the sale of broadcast equipment for Latin America and the Caribbean, and has established and maintained strong relations with customers by understanding and serving their needs. Daniel has been involved in several TV and radio projects as well as the scientific industry. Ladies and gentlemen, Daniel Bizet.
Thank you, Jim, for the presentation, introduction. Good afternoon, everyone. It's really a pleasure for me to be here, and I hope the presentation I'm going to provide is going to be something that you guys are going to like. It's something that Dielectric has been doing for quite a while. I believe that everybody is familiar with Dielectric. Dielectric does, all kind of RF products from the transmitter output all the way to the antenna. So let's go. We're going to start talking this afternoon about the ring master techniques. And before we jump into that, I would like to start by talking a little bit about the historical side mounts FM configuration. We all know that we have been seeing for years, what we have in the market is different configuration. One of them is the full wave, which everybody is familiar. We also have a half wave, an N-1 over N. And this is dependent on the application that we are going to have these different configuration. Well, mostly if we want to have like a broadband antenna, we would normally use a half wave space antenna, no? The one that is the N-1 over N is used only for downward radiation. So if we take a look to the full wave antenna, which this is really a simple of all the options, is something that normally is being used. Of course, this option, it has nearly no bandwidth. It depends on the element that we are using. The bigger the element is, you can get a little bit more of bandwidth. And what I mean with this, a little bit, we're talking probably around, 2 megs, 3 megs, not more than that, no? So the next option that we have that is normally used for us to get bandwidth, and is to have the half wave space configuration, no? So the way this is done is when array brought close together and halfway is when you start having what we call the mutual coupling. No? Coupling stretches the volume, and that increases, the volume increases, and you achieve the bandwidth you're looking for. Then if you go to this next configuration, it's the N-1 over N spacing, and this spacing, it really doesn't give you any bandwidth at all, but it's used only on those cases where you need downward radiation. No? So we call it the funky elbow. If you see just the configuration of the antenna on the middle of the slide, you will see that the rigid line is doing like a zigzag to keep in phase, but shorten the distance between them. No? The downside of using this antenna configuration is you will need 2 elbows per each bay, and of course the cost is going to go more, no? So let's try to put this all together and make it a little bit easier, no? If we go to full wave space, the pros and the cons on each one of them, we will find out that with the full wave, you have the minimum number of elements. Of course, you have the lowest wind load. There is no question about that, but you have limited bandwidth, okay? And you have downward radiation. If you go now with a half wave space, then when you're gonna increase the bandwidth, and of course, you're gonna reduce the sensitivity, especially with the weather, no? There is no downward radiation, and you can get higher power and voltage handling. The downside of using half-wave space is that you have a maximum number of elements, you double the number of elements compared to a full space, and the other thing is that your cost will also go up, and of course, your wind load. And then you have the third option, the n-1 over n space. This is normally used for when you kind of have the antenna on a side that requires no downward radiation. But again, you have limit bandwidth. You have, like I said before, the cost of the elbows and a more connection. And more connection means more failures. So let's say I need a halfway space for broadcast application, but I need twice as many elements and the cost and the wind load. So that's a question that brings up. So can I reduce the downward radiation with less element that have wave space and save money in wind load by losing the bandwidth? So what about if we have a new technology that has a broadband but less wind load and is more economical and can have reduced the downward radiation? And this is when we're gonna go up and talk a little bit about the ring master antenna. This is not a product, this is really a technique, okay? It helps us a combination of half, as you see a little bit on each one of the pictures on the antenna, the combination of half and full wave space base. This technique will help you to reduce the number of bays in the same aperture. And of course, when I mean the same aperture, is reducing the bay, but we will still keep with the same gain of the antenna compared to a half-wave space antenna. It maintains the same broadband characteristic and simply the concept. Like I said before, it's a new technique that we are being using the last year. So we have a different variety of combination on how you can do it. You have not really something particular, it's something that once we are working on a project, we get all the information from the customer, not only from the tower, but all the frequencies, power levels, and all that. So that will help us to set up what are the different models we can use. We have, like I said, like I have in the beginning of the slide, we have the Q, the M, the S, the C, the H. So all of them can be used for this, this technique. So if, for instance, for some reason, we pick up to use the DCRM 6 bay on a configuration of center feed, we can probably choose like having a half, a full wave, full wave, full wave, then half. Or if we have the DCRC 6 with the end feed, it's gonna be probably a full wave and then half, 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 half. So, or we can also have the DCRU. This is an example of 8 bay with dual center feed, and we have a combination of half full, half full, half full, half, you know. So on the right side of your slide, you're gonna see the different combination that we can get from all these type of different bays on different configurations. So as another example, we have the available aperture is 90 feet. So this is, again, a side mount antenna. It's a broadband multi-frequency, and the options we are showing is a 18 bay half wave space, a 12 bay ring antenna, ring master, and a 12 bay ring master with low downward radiation. So you will see that all of them are more or less on the same aperture, but the goal here is that with the 12 bays, we can have the same gain as an 18 bays. So the bottom line is that the Ringmaster design requires 33% less elements than a halfway space antenna, and you still get the same bandwidth. So we think that this is something that, we have been showcasing this lately for different customers. In fact, we already have some antennas on the air with a very good coverage and everything. I'm going to show you an install example. This antenna was, we finished this antenna on July of this year, and it's a DCRU 16 bays. So this antenna is currently working with 13 stations, and all of them are in 1.1 VSWR, and this 16 bay antenna is compared on gain as a 24 bay half space. So that will give you a little bit of an idea how good this technique that we are using, we think it's the right direction to take on Ringmaster antennas. So something that we also have been doing quite a while now is doing the pattern optimizations, and how we're using the new, what everybody call the artificial intelligence approach to pattern optimization and ensure compliance with the license, ERP patterns and limits. So how we do this? This is a computer simulation software. So normally we choose a model from the control library that we have. We run a pattern and compare it to the FCC protect envelope. And, we start moving the bay around the tower and try to look for the best location. Then we check with the FCC compliance, and again, we evaluate if the customer desires a covered requirement. And this is done specifically when we are doing a directional pattern. So we keep that in a loop, and this is where we talk about replacing with artificial intelligence for optimization of the antenna. So how that looks a little bit is you will see all the way on the up, what we call the start is you have the horizontal polarization is in blue, the vertical polarization is in red, and in green we have the FCC protect, okay? Then we start the process, and this is an example we have with artificial intelligence optimization with a C-Bay antenna in a 6.5 feet tower. So the software will start to run, and it will be able to do as much as 320 interactions. So that means if you see on the bottom of the slide, you can see that the antenna is moving around and is trying to match up what is the pattern that needs to be compliant. So that means that it will start doing some offset. Maybe we do some offset with some of the bays, or we start using horizontal or vertical parasitics on the same antenna to try to match the coverage that the customer requires. So this is pretty much done normally in a period of 21 hours. And of course, it's very important for us to have all the information on the tower, because that information is going to be downloaded in the system. And not only the tower information, but we also need to know if there are different antennas or other in the same aperture of the antenna. So the HFSC simulation is a 3D electromagnetic solver. And of course, you have cost advantage because you have no physical model and need to be manufactured and handled like it used to be years ago. We have an accurate reflection, free environment, so no range is truly reflection or interference free. This is something that before, when we do the modeling, it was a little bit difficult for you to get not to be able to have some reflection. That was impossible, no? We have, of course, a mechanical tolerance, a simulation are limited by available of material. This is something that we don't longer have to deal with. Human error, the simulation does not rely on a human to measure. That's something very positive as well. Reproducibility, a simulation provides the same exact calculation every time. So at the end of the story, we find that since we have been using this simulation software, for us it has been a different step compared to what we were doing years ago. We had a personal experience. I mean, Dielectric had a special experience with the FCC because in June of 2021, Dielectric filed a petition of rulemaking with the FCC to allow the use of computer simulation to verify the performance of directional FM patterns. This is something that was not allowed to do before. Even though that on TV it was allowed, it was not allowed for FM. But in May of 2022, the new rule were adopted. So we really feel pleased that in some way we put a little, we help a little bit the industry on this direction. We use this tool as well for, like I said, we have been doing this from 2015, and we have over 2,000 antennas on the field. So that can give you guys an idea that it's something that it is proved, no? So we can figure out here the different patterns of what I'm showing now is a slot antenna for TV. And you can see the different patterns that we have. On the right side of the slide, you will see in red what was the HFSS that we got for that antenna. And then with a drone study, after the antenna was installed, you can see that it matched pretty nicely, no? Same happens down below in the slide. You can see the vertical pattern showing, and it matches pretty smooth. Here are other drone measurement valid that we did. And again, you can see in red the HFSS simulation predictions, and in blue the drone measurement made after the antenna installation. So you see the different patterns that we choose of different projects that we did in the past, and most of them are very accurate. On the right side of the slide, we have again in red what the HFS simulation, and in black the drone measurement, no? And the yellow area that is showing in that slide is the region related to uncertainty for the drone measurements. But definitely this is a technique, a tool that we are being using, and it really, help us to provide a product that really going to meet the needs of the customer. Let's talk now a little bit about combiners. In this case, we're going to go and talk about the manifold combiner. This is another technique that we are being using quite a while ago. It was introduced 3 years ago, if I'm not wrong. And it's a different way, it's a different approach of how you're going to combine stations, no? So the manifold combiner, or the reconfigurable manifold combiner, is a unique package to utilize manifold spline. So incorporate the unused ports for future expansion and analysis used to compute output spline dimension. Again, we use the HFSS for us to be able to determine exactly what is the spline of the combiner. The inputs and output keep the same location and no need to reroute. So what you're seeing on the screen now, you see a bandpass filter that is being pulled out. And this is because we can, let's put this as an example. If we have a combiner for, in this case, we're talking about 1, 2, 4, 5, 7 stations. Let's say that 5 of those stations, we know exactly that they are going on air. But the other 2 stations, we are uncertain if they are really going to go or not on the air. So we can remove the bandpass filter, and afterwards we can replace that with a stub. That way we can have the combiner working on air, and this is also used for you to do maintenance. If you want to do the maintenance of only one of the stations, you can remove that bandpass filter and replace it with a stub. So that's something for you guys to keep in mind. The bottom line of using this type of combiner, you have also a smaller footprint and increase the power handling over comparable designs. So on the mechanical side, you will see that the manifold, we can probably say that it's more or less half the size of a CIF combiner. No? Mechanical is half the footprint. Something very important is that you have fewer parts and connections, so that will increase the reliability of the system. The U-links are easily removed for phase modification, and the footprint remains the same with the addition of future channels. So electrically, talking about all the positions are equal. And in the next slides, we're gonna see the difference between one and the other. We have similar loss, VSWR, and group delays. So the voltage breakdown mitigates by filter size. So when we see this slide and we start comparing a manifold combiner with a CIF combiner, the first thing that we're gonna see is that using a CIF combiner, it decreases the loss farther from the antenna. This is something that we don't see with the manifold combiner because all positions are equal. If you see the losses on each one of the manifold combiner are mostly the same, which is not the case with the CIF combiner. So all the stations are tuned with that VSWR regarding the position they are on the system. So that's another plus of using the manifold combiner. And the voltage limitation by filters mitigate by proper input and output sizes. This doesn't mean that we don't use the CIF combiner. There are, let's say that if we're gonna combine, let's say 4 stations and each one of them are using 40 kilowatts as a TPO, we will need to go to a CIF combiner because we don't have at this moment a bandpass filter that can handle that power input. So if we talk about conclusion, we will say that the manifold combiner is viable alternative to CIF. It has a smaller footprint, fewer parts, so higher reliability. It's equally on the electrical performance, like I showed in the previous slide. Advanced in simulation software allow the increase of efficiency for all possible design scenarios. We also introduced 2 years ago what we call the dual manifold that takes one step further, allowing for increased power handling and flexibility. And we continue to expand the design and technique for the system. This is another example of a system that we achieve, 5 channels. So, sorry. Compact design, we have 5-station manifold combiner, and they include a short with allow maintenance on one of the filters while other 4 stations remain on the air. So that's something very positive to keep in mind of using a manifold combiner. No? The electric to supply spare common parts, and again, we want to highlight the fewer parts and equal more reliability. And this is a little bit what we have been doing for the last 7 years. Different, as we try to move forward and try to see what we can come up with new designs to try to help, to try to improve And I know that physics is physics, but in some way we have the engineering team looking forward to see different options for us to offer customer and make things easier for them. So with this, I will finish my presentation, and I would like to ask if somebody has any question. No questions?
Come on, guys, you got to have lots of questions. I mean, there's a lot of information there.
It is, yes. It is, and it is difficult to put everything together. There are.
Daniel, when you were talking about the AI, can you elaborate a little bit on the power and also the pattern? So, is this something that's automatic? It just tells you, or do you make the?
No, these are special computers that we have, and we have to fill the system with whatever. When I mean fill the system is you need to give all the tower information, and of course we need to know we will have to know what's the CPO of the station. We need to know what's the pattern that was approved by.
So this is actually before installation.
Yeah, all this is done before installation. This is for us to design the system that we're going to provide to the customer.
Okay.
What is done afterwards is the drawn measurement is the customer, if the customer wants to do that.
Okay.
So that the drawn measurement, there are companies that provide that type of services.
Okay. Anybody else? Oh.
Hi, Daniel. I'm just curious, the two, and then I guess the full-length space, and then another one. At what point is it more viable to go that way than just, a standard set of bays? Like any number of bays, or do you need to be up at 10 bays or something like that?
No, there is not a number. For instance, remember that we shipped to Bahamas configuration. If I'm not wrong, it was 6 bays. So that one, we did it, and it was an example that I had on the presentation. It was half, and full. So that one was 5 bays.
Okay. Are those logarithmic?
No, normally.
Or is it just straight?
No, normally it really depends on the frequencies that it's gonna be combined, and what is the best solution for the customer. Because, for instance, in some cases, if the antenna is going to be installed, you need to have a low RFR, then we will go with a dual input. Okay, we try to stay away of the dual input because the price of the antenna will increase. But if the customer requires that, then we have to use that type of configuration, no? Yeah. But there is not something by the book. It's, we need to get the information from the customer, try to understand what they need and what is the pattern they're going to do, because we can combine the frequency, but if we need to do a directional pattern, not only omnidirectional. So there are so many variables that we need to take into account for us to be able to, to come up with the project. So that's why we go with the simulation software, because that will help us to reduce the time for us to come up with a proposal for the customer. And then we start discussing that with the customer. And if he wants to do some changes, tweak here and over there, then we have to go back and, remodel everything until we finally come up with the product and try to keep the customer happy.
Thank you.
All right, Daniel, we want to thank you very much for being here. Ladies and gentlemen, I just want to let you know that, unfortunately, Costa Nichols, thank you. Costa Nichols was supposed to be here during a paper, and I want to thank Daniel because I went to him yesterday just after 5 o'clock, and I said, Daniel, would you be interested in filling in on this paper? So thank you very much. I really appreciate you coming and doing this. I hope you enjoyed it as much as everybody else did.
For me, it was a pleasure really to be here at CCBE, and even though that I don't know very much of you guys, it's is for me. I want to keep coming back every year and, try to see how we can help. Something important I want to let you know is that we work, and I have over there in the back, my friend, we work with Ping Technical Service here in Canada. So if for some reason you cannot reach me, please feel free to contact them directly. Tyler is most of the time the person that
So you can get a
helps me.
hold of them through Pippin.
Yeah.
Okay. Good. Daniel, thank you very much.
Thank you.
Appreciate you being here. All right. Thanks. All right, ladies and gentlemen, that wraps up our papers. I want to thank everybody for coming out this year. Just keep your eyes open. Our website is probably going to be introducing anything else that may come up in the near future, and hopefully we're going to get these papers, all the PDFs and so forth that I get. We'll get them on the website, and I'll let you know as soon as that happens.